some things, what I know about the Big Bang, and hopefully the title of my talk will become a little bit more clear when we move into the subject. And I hope you can all hear me back there. Okay, let me start by giving you some limitations of this talk. And the limitations, some of them are kind of obvious. We only have about 50 minutes, maybe 60 minutes, so it's very hard to talk about everything that we know. And importantly, not everything is known. What I'm going to tell you is still work in progress. We do not have the final word on what caused the Big Bang and what our universe is like. And this may be the biggest stumbling block tonight. I clearly do not know everything that is known. So to put things in perspective, imagine this here is everything that can possibly be known about our universe, and that's correct. This is the truth. What's out there, it's not the truth. So this is what we could ever hope to learn about our universe. What has mankind learned about our universe? Well, we've learned quite a bit. We know that we don't know everything, of course. We also know that some of our knowledge must be incorrect. Because when we take what we know and we extrapolate farther and farther, we run into contradictions. So we know not everything is correct, but we are hopeful at least that we know quite a bit. It's hard to place exactly what we know and what we don't know. And this has not always been the situation. Since the dawn of mankind, when people first stared up, maybe they saw some stars and they saw the sun go up and down, and they figured out a little bit about the world around them. And the rest, river gods, what have you not, right? Not that much was known. But then when more and more time became available to think about our universe, when we could build upon the knowledge of others, at that point, slowly we started learning more. We discovered that actually the Earth goes around the Sun instead of the other way, even though it's almost so obvious that the Sun goes around the Earth, right? You see a dog every day and it goes down. How can that be wrong? I mean, there was a big discovery, actually, figuring out that it's the other way around. Right? So, over the years, over the millennia, more and more became known. And sometimes our knowledge jumps when people like Einstein come along. All of a sudden they have an insight and we learn so much more. We expand our knowledge about the universe, and at the same time we get rid of lots of stuff that turned out to be wrong. It was obvious at the time that people thought it was right, and then all of a sudden it turns out, no, it's wrong. So this is a little bit of where we're heading. And this little block over there is my knowledge. It's not so smooth as the knowledge of mankind as a whole. And I'm not entirely sure of the stuff I know, what is correct, what is not correct. So I'm sort of guessing that I'm probably somewhere around here. I mean, I share some of the knowledge of mankind. I have some notions that are probably incorrect. Because some of the knowledge of mankind is only known to very few people. General relativity, and there's only few people on this planet that actually understand general relativity. I'm not one of them. So, but I still think I understand a little bit. So I'm hoping I'm going to tell you, I'm going to share some of the knowledge of mankind and that I don't stray too far out here. And hopefully there's a little overlap with what's actually part of the truth of our universe. So with these limitations in mind, let's get started. Let's do a little exercise first. Take a moment, maybe close your eyes and picture the universe. Take a few seconds and think of the universe. This is a talk about the universe. What do you say? And perhaps some ideas here of maybe what you saw. This is what I see, by the way. When I think of the universe, I think of stars, endless amounts of stars. And I'm sure quite a few of you thought about stars too. Maybe there's some astronomers or astronomy enthusiasts here, and maybe they have grouped the stars together into those islands of stars, those collections of billions and billions of stars that we call galaxies. And we know we live in a galaxy, and farther away there's countless, well, very many galaxies farther away. So maybe you picture galaxies, or maybe you thought more about planets. I mean, that's definitely part of the universe. We live on a planet, we've explored some planet through robotic missions. It's part of it. Now maybe a few of you thought about this. About us. Looking at those stars. We are part of this universe, right? We are made of atoms that came from the universe, somehow assembled. We have thoughts. We are there. We're part of the universe. When we think of the universe, we should include us too. We are here. Or maybe there's other things you thought of. Did anyone think about this? It's actually not a night sky because there's no stars. This here is space. Space with nothing in it. When we picture the universe, we think about stuff in the universe, but do we actually think about space? Did anyone here picture space? One person pictured space, but kudos to you, that's very impressive. Did you think about this too? Did you think about time? Because, I mean, time, we don't give it any thought. It's just always running away from us, and then every day it's a new day. But we don't think about time, really. But it's part of our universe, just as space is. And Einstein realized that space and time actually are the most important part of our universe. So when we talk about the universe, we have to be a little careful. We have stuff in the universe, stars, us, all the material stuff. But then it's the stuff of the universe, the building blocks of the universe. And until Einstein came along, no one gave space and time any thought. It's like it's always been there. Yeah? Time just goes in one direction, and space has always been there. The stuff moves around in this space. But Einstein showed us that we have to include those. Space and time are actually the building blocks of the universe. That's what this talk is about. When we talk about the Big Bang, we're going to talk about this. We may touch upon something like the laws of physics. For instance, gravity, how things fall. We have laws in our universe that describe how things move. Where do they come from? Are they part of our universe? Are they part of maybe a greater truth? But how things move, forces, it's part of our universe too. Yeah, so let's see let's see where we get to. Time to talk about the Big Bang. Now, you've heard of the Big Bang, otherwise you probably wouldn't be here. And how do we know about the Big Bang? We know about the Big Bang because of observations. When we look at galaxies that are that are different galaxies from our own, we find that they are moving away from us. And whenever we look at any galaxy that's a good distance away from us, we always find that they are moving away from us. This was discovered by Edwin Hubble and Georges Lemaître. And when you do observations, you will find another astonishing fact. You will find that not only are galaxies moving away from us, and I apologize for the crude drawing of galaxies here, but you find that if you take a galaxy and you measure how fast it's moving away from us, that a galaxy that's twice as far away is speeding twice as fast. A galaxy that's 100 times farther away is moving away 100 times faster. This is what you'd expect if you had an explosion. Imagine you have some fireworks or something and shrapnel flies off. When you observe it a little bit later, stuff that's still pretty close is not moving very fast. Stuff that's twice as far away from the center of the explosion is going twice as fast. That's how we cover double the distance by going twice as fast. And amazingly, galaxies do this. Whatever galaxy we look at out to billions of light years away from us. And a light year is a distance that's really big. This is a scientific okay. All the galaxies that are moving away from us, they have this relationship. If you go away 10 times farther, you find that the galaxy is going away 10 times faster. It looks like there was an explosion in the past, and we are right at the center of it. These are observations. Okay, well, you can do something then. Once you have this, you can ask yourself the question, where were these things located about a year ago? They were a little bit closer together. How about 10 years ago, 1,000 years ago, 1,000,000 years ago? You can run the clock backwards until you find the point that all these galaxies are together. And all the matter is in the same spot. And when you do the math, and it's not very complicated really, you just run the clock backwards, you find that 13.8 billion years ago, everything was at the same point. That's when the explosion that we now see the effects of must have happened. And this is called the Big Bang. Just running the clock backwards, you can reason that everything must have been in fact together. And if you run it back all the way, everything must have occupied a really, really small space. In fact, smaller than the size of the smallest thing you can imagine, a proton. All this must have been, all the material of the universe must have been there. That's what the observations tell us. And based on these observations, the Big Bang model was developed. And this model, when you do your calculations, you come up with new predictions. And these new predictions you can test against new observations. And all these predictions of this model were verified by observations. So now we call this the Big Bang theory, because it predicts what we see. It seems to describe. Did I say something wrong? So let's look at the Big Bang. I mean, it's great for me to say, okay, 30.8 billion years ago, everything was together. But I mean, how? What? Why a Big Bang? What happened then? Really? So we're going to look at these things. We're going to look at them together. I'm first going to do the most easy question. That's the what. How is it connected to what we see? What actually happened when we look at the details of how things were together and then they're not, and now we have galaxies speeding away from it? If we apply what we know about our universe, about the laws of physics, how do you go from everything together to what you see now? That's the what. And this part actually is under control. We physicists, astronomers, cosmologists, we understand it. So I'm going to walk you through it, and it's going to take a little while, 10 minutes, 15 minutes, something like that. But imagine that you have a certain amount of energy, heat, whatever you want to call it, and you make it expand. What's going to happen is that things are going to cool off. If you spread out energy or heat over a larger volume, there's less available per volume. Things are going to cool off. Conversely, if you're going to compress things, if you make things contract, you're going to heat them up. That is this relationship. If you spread things out, it's going to cool off. If you bring it together, it's going to heat up. It's how our refrigerators and AC units actually work. Okay. Well, if everything, our universe is pretty big, let's face it, right? So if we bring all that stuff together, it must get much hotter. In fact, if we bring everything together in one point, it must get unimaginably hot. There's no way around it. And when things are really hot, we know this from experiments, when things are really hot, it means that whatever is there, like these little particles, that they are moving around like crazy. This is actually what temperature is. Temperature is just a measure of how things jiggle. If things warm up, they jiggle more. If things warm up a lot, they jiggle more, and solids will melt, because things don't stay in position. And then you get liquids, and then it becomes a gas, and you heat it up more, and things start moving around more and more, and they collide with each other, everything that's in there. You get collisions with like high energy collisions. And when you smash things into each other at very high energy, they break. Really, you get it. So the universe was so hot early on, and everything was smashing into each other that everything was broken. Nothing stuck together, it was that hot. So the only thing that were left were the things that could not be broken. And we call those elementary particles. Elementary particles are little things that have no internal structure. You cannot break them apart anymore. So very early on, right after the Big Bang, it was so hot, nothing could stay together. The only thing we have there are elementary particles. And physicists like that, because it's complete chaos. If nothing sticks together, you just have a bunch of particles all colliding. You can actually describe it really well. It's not that difficult. It only gets complicated when things start sticking together. So that state, very early on, we can describe very well with what we know about physics. And to give you an idea of what elementary particles are, I mean, let's say this is the table you're leaning on. If you look very closely, you'll find that there's atoms inside the table. And for the longest while, people thought that atoms, those are the little building blocks. You cannot break apart an atom. But then, it turns out if you smash two atoms together fast enough, they fall apart. Atoms themselves are made up of smaller particles. They have a bunch of electrons, and at the center of the atom is something that's called a nucleus. People have smacked nuclei together to see if you could break them too. It turns out, yeah, you can break them too. They're made up of smaller particles called protons and neutrons. And it turns out if you smack protons and neutrons together, they also fall apart into smaller building blocks. All the way until you reach something that we call quarks. And as far as we know, you cannot break those apart. Maybe you can if you try even harder, but with all the energy we have available in our labs, we cannot break a quark apart. So we call a quark an elementary particle. And the same actually holds for an electron. It looks to us like you cannot break an electron apart. It's an elementary particle. So this is the early universe. The Big Bang has just happened. I'm not saying why or how, I'm just describing what is going to happen next. Big Bang has just happened. Really hot. So nothing sticks together. We just have elementary particles, quarks and electrons. That's where our story starts. And somehow our planet comes out of this chaos. And I'm going to start my story 1/10 of a nanosecond after the Big Bang happened. And a nanosecond, or a tenth of a nanosecond, is a real short amount of time. To give you an idea, this nice little laser pointer, if I shine it at the moon, the light will get there in 1 second. If I instead look at 0.1 nanosecond, the light will only travel 1 inch. That's how short the time I'm talking about right after the Big Bang. And the reason I picked this time is because we physicists, cosmologists, are pretty sure, actually almost confident, that we can describe the state of the universe at this point in time and take it all the way to the galaxies. What happened before it, we're not so sure about. We have not theories but models. And before that, even closer to the Big Bang, our models become educated guesses. But that's the reason I'm going to start at this point. And to give you an idea, here, this is where the Big Bang happened. And time goes this way, and it's a very peculiar time scale. It's not linear, it's not like 1 year, 2 years, etc. No. This is here my 1/10 of a nanosecond. Here, the universe is 1,000 times older. Here, it's another 1,000 times older yet. Here, it's another 1,000 times older. Here, we're talking about a millisecond. So every step here is when the universe gets older by a factor of 1,000, an enormous amount of time. And here's where the story starts, where the universe is so hot, everything's together, that only elementary particles exist. And then the universe will start to expand. Things will move away from each other. And when that happens, the universe cools up. Because all this energy is now spread out over a larger volume. You can see how the universe is going to cool off. So we're going to take the story from here. We're going to follow the cooling off of the universe. And we're going to go all the way to galaxies. That's the what part of this whole. Okay. Here are my elementary particles, little quarks. Quarks like to stick together. They like to stick together in groups of 3. And here's a group of 3 that's a neutron. And another group of 3 with 2 darker ones and 1 lighter one is what we call a proton. Quarks do that. They stick together because there's a force between the quarks. And this is a really strong force. And we have a very good name for it. It's called the strong force. And these quarks like to stick together and they like to form protons and neutrons. But it's still really hot. They still smack into each other, and even when they form, sometimes they fall apart. But at some point, the universe has cooled off so much that these collisions are a little less energetic. When the temperature is about 1 trillion degrees, actually that's the point where these quarks can stay together and form these new particles. And these new particles don't move fast enough anymore than when they collide that they break apart. So we know this because we can do this in our labs, actually. We can make things hit each other with such great speeds that they fall apart. So we are confident. And at some point in the history of the universe, where it cooled off enough, you will see that things start sticking together. In fact, this strong force, you can picture it as glue, actually, as a layer of glue around the quark. When you stick 3 quarks together, you can get a neutron or a proton. But some of this glue actually is still available on the outside of this entity, this new entity. Not as much, but neutrons and protons, they can stick together because there's a little bit of this glue left. We call it the residual strong force. And because it's only a little bit of glue left, it's not as strong. But these things still like to stick together. But it's easier to break them apart in collisions. So the universe needs to be a little cooler before these things stick together. It needs to cool down to a mere billion degrees, from 1 trillion to a billion. I mean, these are meaningless numbers, right? You know, like million, trillion, whatever. But we know those numbers. I mean, we measure them. And what I've drawn here is a nucleus of a helium atom. And this stage was reached 5 minutes after the Big Bang happened. This little stage before, when quarks started sticking together in protons and neutrons, that only took 1 millisecond, and the universe had already cooled off that much. But then if you wait 5 more minutes, you'll find that those protons and neutrons also start sticking together and form new particles. And this is the state of the universe after 5 minutes. There is a much inner universe, actually. There's electrons. They're still zooming around. And there's a bunch of helium nuclei, and then there's some leftover protons, actually a lot of them, that did not find anything to pair up with. They're still here today, actually, those leftover protons. Those leftover protons, they became hydrogen. This here became helium. And that's all there was in the universe after 5 minutes. There was nothing else. There was no carbon. But we understand this because we actually do this in our labs. We can break apart nuclei of atoms and see what temperature is required. So we understand these things. And we have associated it with this strong nuclear force. By the way, you may ask, why have I never heard of the strong nuclear force before? If it's so strong, how come I don't know it? I know gravity, I know the electric force maybe a little bit, but how come I don't know about the strong nuclear force? Well, the reason is because it's too strong. In our everyday life, these nuclei, they never break apart. I mean, even when two football players hit each other, there's not enough energy in this collision to actually do something to the nuclei. They are bound together so strongly. In our everyday life, they never fall apart. That's why we don't notice this force. But there's more forces. There's also something called the electric force. The electric force is not as strong as the strong force. It's about 100 times weaker. But it's still a respectable force. And what the electric force does, it attracts electrons to protons. They both have an electric charge, maybe you've heard of it or not, but there's this attraction between protons and electrons. And electrons like to stay with protons. And when that happens, we call this new entity an atom. But this force is not very strong, so even when these atoms form, and you smack them into each other, they can quickly lose their electrons again. But when the collisions get less and less energetic, which happens when the universe gets bigger and bigger, when it cools off, you have to reach a point where the electrons can stick around with their protons, that you actually have atoms. And this point happened after about 400,000 years after the Big Bang. Again, we fully understand this. We know all about the electric force. In fact, even though this force is pretty strong, I mean, we can sometimes rub some electrons off ourselves and put them somewhere else and see how they are attracted back, and then we get sparks and all these things. We can do that. We understand this force, and we understand that once the universe cools down to below 3,000 degrees, that we have atoms. Not exciting atoms, though. We have hydrogen atoms and helium atoms. Now, why is this important? This is a very important stage in the history of our universe. Because, I've said there's elementary particles, there's electrons and other things. But there's also light. I didn't mention there was light, but there's a lot of light. Imagine an explosion without light. What's the fun in that, right? I mean, there's lots of light flying around. And light has an interesting property. It can actually collide with an electron and change direction or be absorbed. In fact, that's how light is generated. You get light by taking the electron and shaking it like that. And when you do that, light comes off the electron. That's how the sun gives us light. In the surface of the sun, you have electrons going like this. And when it happens, it gives off light, and that's the light we see. And we understand that. But when you have those electrons, the opposite can also happen. Light just gets scattered. And the universe is opaque, because light cannot get from place to place, because you have all those loose electrons. But then, when those electrons became part of atoms, all of a sudden they weren't loose electrons anymore. And you didn't have this scattering mechanism. And all of a sudden, light could stream freely from one end of the universe to the other end. The universe became transparent. And to this day, we can still see that light, even though it was emitted 400,000 years after the Big Bang, essentially 13.8 billion years ago. We can still see that light. Wherever we look, in whatever direction of the universe, we see this light still coming towards us. And the reason it's still coming towards us is because it had so far to travel. It's been traveling 13.8 billion years just to reach us. But we still see this light. And it looks the same everywhere in the universe. In fact, light tells us a lot. The color of light tells us something. The color of light tells us how hot the object was that emitted it. Think about it. The sun is a certain color, yellow, because it's 6,000 degrees. But if an object is less hot, let's say an ember in your fireplace, that's much less hot than the sun, it gives off a different color. It glows red. And if you look carefully at the color of the light, you can figure out the temperature of the object that emitted it. So this light comes from everywhere. It's called the cosmic microwave background radiation. You may have heard of it. We find it everywhere. It's light that was emitted so long ago. And it's the same everywhere. It's the amazing thing. Because if you have a Big Bang and you have this explosion, you expect things to be the same everywhere. Really. And when you look at where the light comes from, it comes from all directions evenly. And it's the same color. Meaning that when it was emitted, the whole universe had the same temperature. And that's one of the predictions of the Big Bang Theory, is that you should be able to observe this light if this theory is correct, and it should have the same color. So this is it's proof of the Big Bang. But there's more. I said it's the same color, meaning the objects had the same temperature. Well, that's almost correct. There's a tiny variation in color, meaning there was a tiny variation in temperature when it was emitted. And it's tiny. It's 1 part in 100,000. And here, this map, the dark bits correspond to temperatures of 2.7349 degrees, and the other ones to 2.7351 degrees. Now let me tell you something about the temperature scale, because it's a scale in Kelvin, which is what scientists use to denote the temperature of something. Like, it's a very special scale. It's a scale that starts at 0. Because temperature is how the jiggling of particles. And when you cool them down, they jiggle less and less and less and less. There's going to be a point where they're going to jiggle as little as they're ever going to jiggle. You cannot slow them down anymore. And that point is the 0 point on this very special temperature scale called the Kelvin scale. To give you a reference, in our room here it's 300 Kelvin. So there's a lot of jiggling happening here. We could still cool down a little bit. But when you look at the temperature of the universe as it is now, you'll find that the universe has a temperature of 2.7 degrees with tiny variations. Now, why am I boring you with talking about variations of 1 part in 100,000? It's because these tiny variations are going to turn into galaxies. What I have here is nothing much, just atoms, hydrogen and helium. But what is temperature? If something is a little hotter, it moves a little faster, it requires a little more space. Something that's hot has a little lower density than something that is cold. When something contracts, all the atoms sit together a little bit closer, you have a little bit higher density. You know that when things expand, they get big. When you heat up things, they get bigger. This here, everything is almost the same temperature, except some regions are a little hotter than other regions. Meaning, these regions are a little bit more dense than those regions. Now, this is where the next force comes in, the force of gravity. The force of gravity is a weak force. It's not strong at all. I mean, we need the whole Earth just to pull us down. Look at all the mass in the Earth, and you still can escape it a little at least. It's a weak force. But if there's a little bit difference in density, it means you have a little bit more stuff here than there. And what's going to happen is that things are going to fall towards the region where you have a little bit more stuff already. It's going to take a while. As things will fall slowly, the force of gravity is weak. Those differences in density are minute. But if you wait long enough, it's going to happen. Things are going to fall. if you wait about 1 billion years, what you're going to see is that those dense regions have gotten much more dense. And the less dense regions are almost depleted of particles. Things have lumped together. When you look after about 1 billion years, you will find that you have enormous clouds of hydrogen and helium that have lumped together. And a cloud like this will turn into a galaxy. It's a process we understand really well. If you have something, a cloud, and everything attracts each other because you have this force of gravity that we're so familiar with, this cloud will try to get smaller and smaller. But at the same time, this cloud is moving around a little bit, it's rotating. So you have something that's trying to get smaller and rotating. And what's the end result? We call it a pizza. Like if you ever bake a pizza, you start with a ball and you swing it around and you end up with something flat. It's the same principle. This has to end up being a pizza. And we call those pizzas galaxies. And it's a process we understand really well. We know time frames for it, and if you wait 1 billion years, or maybe even a little shorter, you end up with matter that has clumped together because of the force of gravity. And we understand much more. We understand when these clouds contract, or when a small region contract, when everything gets closer and closer, it heats up. Right? When things contract, it heats up. And it can heat up so much that actually it can ignite, that fusion can start again. That's based on this strong nuclear force. And you get stars. It's a process that's really well understood. And stars are essential to us. Because up to this point, we just had hydrogen and helium. We're carbon and other stuff. Where did it come from? Well, it's the stars that fuse helium atoms together to form carbon, oxygen, magnesium. In fact, everything other than hydrogen and helium is made in stars. Most of our atoms were created inside old stars, dead stars. But believe it or not, this process is understood. Once the strong nuclear force was uncovered, and it was understood how stars can do it. It's not a mystery. In our Watt description of the Big Bang, we actually understand how you go from elementary particles all the way to galaxies, to stars, to all the atoms, elements that we need. Which is an incredible accomplishment of mankind when you think about it. That we know so much about stars without ever having been to one even. We know all that. Okay, now there's one detail that's very important, but it's sort of glossed over, and that is these things, these little variations in temperature, that became the seeds of galaxies. Planets, stars, everything. It's contained in this map already, this photo of our universe when it was only 400,000 years old. But where do these variations come from? Why do you have these variations? Why is it not exactly uniform? Because that's important to our existence. If it had been uniform, gravity didn't know what to do. We wouldn't have galaxies and stars and elements. Now, this is also something we understand, but only partly. There's one thing we understand, variations we understand. Picture the air in this room. Okay? By and large, there's just as many air molecules here as there are here. But when I look really closely, there's going to be a little bit of variation. Maybe I have 1 million molecules here, and 1,001,000 here, maybe a few more. And this makes sense because air molecules, they just move around randomly. Sometimes more come here, sometimes more go here. If I take a snapshot, I'm going to find some variation. It's small, being by and large, it's the same number everywhere, but there's going to be a little bit of variation. And everything in nature has that. There's always some variation associated. Even with the very early universe, when we just had the Big Bang, there must have been a variation. Maybe a variation in temperature, maybe a variation in density, but it's inescapable. So we understand that, and then this variation of 1 part in 100,000, it makes sense, actually, that number. We're not surprised by that. But there's a little thing we swept under the rug here. Here's the Big Bang. This is little variations of something. I'm not even telling you what it is. And then 400,000 years later, we have atoms with little variations in temperature. This is where our Big Bang theory becomes more like a model at this point. Because to go from there to there, there's a little bit of a problem. Our room has the same number of particles everywhere because everything is in contact with everything else. This particle can go all the way over there. If wait enough time, it can go over there. Things are in physical contact with each other. But at this point, our universe is already so big, has expanded so much, that this is not in contact with that. It even takes light longer than 400,000 years to go from here to there. Which is a puzzle, a problem, because you only expect the same temperature for something that's in contact, right? Like we have a different temperature here than we have on the North Pole, because we're not in direct physical contact. It would take a while before things to even out. The universe here is too big. It shouldn't have had the same temperature. But it does. That's an observation. So, how do people get around this problem? Because it's a real problem. And the idea to go around it is called inflation. That was proposed by Alan Guth in the early 80s. It's a beautiful idea, and it may even be testable sometime soon. But the idea is that the universe, after the Big Bang, was gently expanding. It was very small, everything was in contact, you had these variations, and then poof, magic happened. And all of a sudden it got much bigger. And this magic is called inflation. And I call it magic, but I shouldn't call it that. Because we can actually find it in the laws of physics. What mechanism could do this? Our problem actually is that there's more than one way to come up with this mechanism in the laws of physics as we understand them. You know, we have too many options here. We don't know which one could have happened, or maybe another one we haven't thought of. Yeah, so that's why the stage from here to there is still a little bit of modeling, speculation, all these things. But it does explain why you have these tiny variations. They go back to right after the Big Bang, when everything was in contact, then it just blew up, and the variations blew up too in size. Those minute, very small scale variations became large scale variations. That became galaxies. And so the galaxies were already contained in our universe an instant after the Big Bang. All the information was already there. Okay? And we're getting so close to actually understanding this step too. Right now, I started at 0.1 of a nanosecond. That's already a long time after inflation happened, which happened well before 1/10 of a nanosecond. But slowly but surely, the boundaries are being pushed back. And as I mentioned, we understand everything after 1/10 of a nanosecond. We understand how you get galaxies after about 1 billion years. And indeed, when you look very far away, you can see galaxies that formed within 1 billion years. I mean, if you look very far away, it takes light so long to travel to us that we're looking back in time. Our Hubble Space Telescope actually sees these things. We understand practically all of the world. Now the how. Thanks to Einstein, we also have learned a great deal about the how. You've probably formed a mental image now of the Big Bang, of things. Expanding, right? This image is wrong. And I'm sorry, I deliberately installed it because it's so easy to talk about. But that's actually not what the Big Bang is. That's not how the universe got larger. Because this image is the universe expanding into a pre-existing space. Like space was already there. Was always there, just like time, and then this Big Bang happened and things just flew away into this space. This is the wrong picture. Einstein taught us that. Actually, what happened in the Big Bang was that space and time were created. When I talk about the expansion of the universe, it's actually space that expands. If I have two objects this far apart, they look to us like they're moving away from each other in a pre-existing space, but when you look closely, it's actually more space gets added between those 2 points. Space grows. Space is dynamic. When we think of, well, whenever we think of space, we think of it as it's there. But Einstein discovered that space, you can stretch it, you can morph it, you can create it. It can disappear into black holes, actually. Space is something very special. And now our understanding of the Big Bang is, it's not an explosion in space. It's an explosion of space. And this is so difficult to picture. I mean, try picturing space. It's nothing. And then try picturing more of this nothing. I mean, how can you do that? Mathematically, actually, it's a little easier than to get your mind around it. But this is based on knowledge, it's based on experiments. And to this day, space still expands. We see galaxies moving away from us, not because they're actually flying away. No, it's because more and more space gets added in between the galaxies. That's the how. It's still not the why, right? It's based on observations. And inflation is, what's inflation? It's just space going haywire. Making so much new space at an incredible rate. The universe doubled in size so many times in a jiffy, which is even shorter than 1/10 of a nanosecond. In a jiffy, the universe doubled in size 100 times. It's not it got 100 times bigger, no. It doubled in size, it doubled in size, it doubled in size, it did that 100 times in an instant. That's what inflation is, that space goes completely bonkers. And you can see that it's difficult to test, right? And if you have such a crazy notion, how do you even test it? Actually, people right now in the South Pole, they're doing observations of light that reaches us, and they look at specific properties of the light, and the imprint of inflation may be embedded there. So actually, what I'm telling you, and I'm not sure if you believe me or not. Maybe you're thinking, my knowledge right now is firmly into the blue part. I don't know. Let's talk about space a little bit more. So we discovered that the universe is not static. It grows, it expands. This was a major discovery, because when you look at the night sky, if you ever do that, things don't change very much, right? I mean, you see the stars, and okay, the stars rise and set, but if you take out the fact that the Earth is spinning, the stars pretty much stay there. Right? Especially if you do one orbit around the sun, you come back a year later. Hey, all the stars are still there in the same positions. It looks like nothing is moving. You have to take such accurate observations over such a long time to actually figure out that things are moving, that the positions of galaxies and stars are not steady. But there's more. It's actually the space in between these things that gets larger and larger. We have discovered that now. And so when you hear about the expansion of the universe, it is space that's expanding. So here's a little cartoon. Big Bang, yay. Galaxies formed about 1 billion years later. Here we are now. 13.8 billion years later. During this time, the space in between galaxies has expanded. That's why the galaxies are moving away from us. Now it gets tricky. Why? Why on Earth would space do that? Why would space just make more copies of itself, so to speak. So let me tell you a little bit of physics. Now, when you have something in nature, you have a certain energy associated with it. Maybe you have a picture of what energy is. Energy is a number that's useful because if you have a lot of energy, you can do work. Right? It's something good to have. And in nature, objects like to lower their energy. For instance, I'm not going to do it here, but if I were to drop this fine, expensive laser pointer, it would fall to the ground. Why does it do that? Because it's losing some of its potential energy. It likes to lower its energy. Everything in nature likes to lower its energy. But here's the trick. All our stuff that we think of, matter, all these things, motion, they have positive energy. And think of energy as this number, it's something good, you can do work with, it's a positive number. Well, not so for space. Space has negative energy. Which is kind of, don't know what to picture there, to be honest. But Einstein told us space has negative energy. I'm not going to argue with Einstein. Right? Okay. Here's zero energy. Here's things that have positive energy, like this laser ball. Pretend that here I have negative energy. This is where space is. Okay, space has negative energy. What would space like to do? Lower its energy. It's still subject to that law. It would still like to lower its energy. Well, how do you do that? Just make a copy of yourself. Needs negative energy. Now it's more negative. Make another copy. It's more negative. That's the equivalent of a laser pointer falling. Space creating copies of itself. It does that because space has this crazy thing, this crazy property that we call negative energy. Hey, they're going to say, like, yeah, that's not really why, it's just rephrasing something stupid into something silly. But you can do experiments. I mean, you can write down the equations and it makes sense. And you can test those equations because they don't only predict that space makes copies of itself. No, there's many other predictions. And these are all due to Einstein. And they have been tested, verified experimentally, over and over again. And so let me tell you what Einstein discovered. Einstein discovered that space and time, that we think of as completely separate things, are actually linked together. When we think of space and time as separate things, what I mean is that my clock here will run at a certain pace. My clock here will run at a certain pace. And no matter how much I jump up and down, my clock will keep running at a certain pace. It's not related in our everyday experience to anything we are doing or where we're doing it. Now, Einstein discovered that this was wrong. It seems so obvious, but it's wrong. It's like the sun going around the earth. No, it's not the case. Einstein discovered that it just seems like that to us because we are moving so slowly. When you really speed things up and you make stuff fly close to the speed of light, you will find that things change around. You will find that clocks slow down compared to clocks that are not moving. And that even yardsticks, rulers, that they shrink when you move fast. And this is fact. We have stuck very accurate clocks on jets and make them fly and then compare them to clocks we have on the ground and we find that actually, yeah, they're no longer synchronized. There's a difference. Einstein was right. There's so many of his predictions and they all say the same thing. They say space and time, they go together. We think of them as separate, but it's an illusion because we're moving so slowly. But under extreme conditions, going fast or falling into a black hole, something really extreme, you can see that they are mixed. In fact, when you fall into a black hole, just before you disappear over the horizon, your clock starts ticking so much slower and slower and slower. You can see that. Well, not that we've thrown anyone yet into a black hole, but and actually when you fall into the black hole, space and time will switch around. They are that linked together. Once you're inside the black hole, space only goes in one direction, to the center of the black hole. Right now, time only goes in one direction, right? We cannot turn back time. Inside the black hole, we cannot turn back space. Einstein figured this out. And space and time, they go together. Now imagine this. You're not surprised to learn that there's more and more time in the universe. Every day there's one more day. Right? Time has expanded in our universe. Well, if space and time go together, then, yeah, of course, space also had to have expanded if they really go together. It's a different way of looking at the Big Bang. Expansion of space goes hand in hand with more time. And this is why I called my talk The Day That Time Began. Because when we run back the clock and we run out of space, when everything is together, then there's no space. There also is no time. You cannot separate the two. You have both. We call it space-time. But you cannot separate them. So, before the Big Bang, there was no time. In fact, I cannot say before the Big Bang because that refers to time. There is no before the Big Bang. In the Big Bang, space was created and time was created. And then space went a little bit crazy, and then matter appeared. And believe it or not, we actually understand that a little bit too. Because there's a law in nature that says conservation of energy. What that means is that you do something and you have a certain amount of energy before you do it, and whatever you do at the end, you have the same amount of energy, maybe redistributed. But there's that law that says conservation of energy. Well, the universe also obeys this law as far as we can tell. So imagine this Big Bang. Space went haywire. You're creating a lot of negative, more and more negative energy. You cannot do that because you need to have as much energy before as after. So at some point this had to go wrong very quickly. Positive energy had to balance it so that in the end you got nothing again. If you started with no energy and then all of a sudden, ooh, negative energy, you have to balance it with positive energy. And this positive energy, we call it matter. Those are the elementary particles. They had to appear because of what space was doing. I'm not sure everyone believes me here. Let me tell you something more. When you add up all the negative energy of all the space, this expanding space, all the stuff we see around us, all the stars, everything we can find, when we add up how much negative and how much positive energy there is, it really appears to add up to zero. These two really appear to balance each other, which is extremely lucky for us and extremely important, because this is our universe. I mean, I told you what, how things slowly group together and form these galaxies. Well, the force of gravity is weak. It needs some time for things to fall together. Imagine space had expanded just a little faster than it did. Then those atoms that are trying to group together, they would be a little farther apart. The force of gravity between them would have been weaker. And in fact, it would have been so weak that these clumps, these galaxies, could not have formed. Just if space had expanded a tiny, tiny, tiny bit more rapidly. Or if space had expanded a tiny, tiny, tiny bit less rapidly, then the force of gravity would actually have put everything together. And all the stuff would have fallen together, and we would have ended up in a big crunch. Like a gigantic black hole, all the space would have been eaten up. This is called the Big Crunch, and this is just called darkness. But we were so close to either scenario. But luckily, we were there. And in fact, we were extremely lucky, because the force of gravity and the strong force, the electric force, they all have just the right ratios of how strong or how weak they are for things to be just right. For instance, our sun is going to shine for 10 billion years in total. We're halfway there. If the electric force had been a little different, the sun may already have run out of hydrogen. I mean, we wouldn't have time to evolve from bacteria into people. And so all this, it seems to be extremely lucky in our universe that things were just right. We don't know why. It's an observation. it's directly linked to the Big Bang. We understand a lot about the Big Bang. It's related to space, the property of space, this thing we never give any thought about. How it's related to time. And we understand so much. And then it seems like there is this big thing like, why was the Big Bang that big? Why was it not a little smaller? Why were there 100 doublings of the size of the universe instead of 101 or 99? In which case we wouldn't be here to ask that question. And so we have different questions now. So, I'm almost done. Almost done. Let me give you a summary of what I've talked about. Big Bang, it's fact. Galaxies are moving away. There's very few people who doubt and actually see the data. It's very hard to ignore. And this came with predictions that were verified. It's a thing now. It's not complete because, yeah, we can trace it back all the way to 1/10 of a nanosecond, but this inflation thing, we still need a bit more evidence for. It's a luxury problem. There's too many ways that space could have expanded. There's too many triggers for it. And an important thing is that the Big Bang was an explosion of space, not an explosion in space. But there's still some really important questions. What caused the Big Bang? Because I said I had nothing before, and then negative energy, positive energy, expanding space, matter, sticking together, forces, all these things. But I started with nothing. Why did it go so bad? Why did it go so crazy? And the answer to that is, we really don't know. We have no idea. And it's a very deep question, because suppose our understanding of the laws of physics becomes so good that we find somewhere in the laws of physics why the Big Bang happened. Then the question is, why if the laws of physics describe it, it's a natural phenomenon. Why would it happen only once? What's a natural phenomenon that only happens once? Natural phenomena, they happen many times. There should be many Big Bangs. Is that what happened? And let's skip those, but if the Big Bang is contained in the laws of physics, where do the laws of physics come from? Were they there before the Big Bang? Yes, that's just moving the problem, right? Even if we understand the Big Bang based on the laws of physics, then where do the laws of physics come from? How do you answer this question? And so, another question that people are pondering is, why is the universe so bio-friendly? Why is everything just right for galaxies to form, stars, new elements, us, planets, all these things, everything is just right for us. I mean, it's so unlikely, actually, not just that the expansion of space was just right, but that all the forces had just the right ratios. And I may have an answer for you, but maybe not. So I'm going to close with a little bit of hands-on experiments, because I'm told you always have to do that in good presentations. So let's do it. Put your hands together like that, but make sure there's some room inside. Okay, what do you have inside your hands? Air. Let's get rid of air. Let's suck it out. Let's suck really well. Let's get rid of all the air. Maybe we're really good at it. Maybe almost all of it is gone. Maybe there's just one proton left, as there is in outer space. Yeah, but let's pretend it's gone. What do we have now in our hands? Is it empty space? We have space, but is it empty space, or is there still something in it? There's still something in it. For instance, the magnetic field of the Earth goes straight through it. That desktop there is generating the electric field that goes through it. There's a gravitational field, there's the Earth there. There's no matter, there's still an influence that we call fields. There's also fields that are invisible, like the Higgs field, you may have heard of these things. There's still stuff in it, it's not empty space. Let's get rid of this stuff. Let's shield this magnetic field. We can do that. Shielding magnetic field is not that difficult. I mean, if it's caused by some big bar magnet, you just take the opposite bar magnet and they will cancel each other. Let's do that. Alright. We shield the magnetic field. Let's do the same for the electric field. We can shield that well too. Then we just apply the opposite field. We have that technology. Gravitational field. Let's get rid of it. Let's just apply some anti-gravity. Okay, maybe anti-gravity doesn't exist. If it were, then I wouldn't pay so much on my airline tickets, I imagine. But there actually is a way that gravity can be counteracted. Maybe a supernova explosion went off somewhere, and when that happens, there's actually a wave, a gravitational wave that goes through space. And what it does is it stretches space, it compresses space, it stretches space. If that wave maybe goes through my hand and it's trying to stretch space, it can counteract what the Earth is doing actually. Einstein told us that what the Earth is doing, it's also playing around with space. It's morphing space. And maybe by chance, the two effects can cancel each other. It's unlikely, right? But maybe it happens. What about those other fields that we've not heard of yet? The Higgs field, more and more fields. We also have to cancel those. Well, we have no clue how to do that. So I don't have any space. But it could happen by chance. Don't picture a large volume like the stuff between your hands. Picture a real small volume. This is the smallest volume you can imagine. And then make it smaller, smaller yet. Now we have a tiny amount of space with some field things going through. But now by chance it's much easier for all these fields to cancel each other. To cancel something, we just need the opposite. Maybe the Higgs field says, oh, it's 4 there. And then by chance, maybe a little variation comes along. We should always have variations in nature. We cannot avoid that. Maybe a little variation comes along that says -4. The 4 and -4 cancel. And in this tiny space, we're rid of the Higgs field. It's unlikely, but it could happen. Imagine that every field was cancelled in this tiny space. What do we have now? We have empty space. Truly empty space. Now, empty space is about as stable as an NFL player in an elevator. Empty space goes haywire. It will just expand like crazy. That's what Einstein told us. Right now, somewhere inside your head, by chance, space could be expanded. A new universe could be going off in your head, a Big Bang. And you would not know it. Because you think of like, oh, wait, the universe in my head should split apart. But that's not what expansion of space is, no. I mean, from our point of view, things just look to be at the same distance. But somewhere inside there, space is being generated. If you were inside there, you would see there's all this new space. But it doesn't affect the stuff outside. A Big Bang can be going off anywhere and you wouldn't know. I mean, the one I just talked about went off about 2 seconds ago. Right? We already have protons trying to stick together with neutrons at this point, trying to form nuclei in this new universe that's happening inside your head. It's very well possible. But now we may have a solution out of the conundrum of why is our universe so bio-friendly? Well, if this Big Bang really is so easy to create, and we would never know whether it happened or not, whether it's happening right now inside my head. You're probably thinking, well, it happened quite a while ago inside your head. But a lot of those universes will not be suitable for life. The expansion rate of space may have been wrong, or maybe the electric force may have been too strong. Most likely, all of these universes, the gazillions that are being created, all of them are probably lifeless. But sometimes by chance, maybe this expansion of space was just right. Maybe the forces were just right for something to happen like in our universe. Yeah, for space to expand at just the right rate. So it may have been very unlikely, but as long as I have enough of those Big Bangs, and this collection of Big Bangs is called the multiverse, in case you read it in paper. But if I have enough of those, then one of them is very suitable to life. And of course, that's the one that we're living. Otherwise we wouldn't be asking those questions. So this may be correct. When we learn more about the Big Bang, maybe we can tell the answer. Is the Big Bang dead? Does it still happen? Okay, I think I should stop here. Thank you very much.